everybody. In this video, we're going to use the cheapest link algorithm to approximately optimize a Hamiltonian circuit in a complete graph. So take 3 deep breaths and let's make this math easy. All right, so the cheapest link algorithm is a way to solve the traveling salesman problem approximately. Because remember, the only way that's guaranteed to find the absolutely cheapest Hamiltonian circuit in a graph is with the brute force method. But the brute force method just takes so much time that it's not very efficient. And so sometimes we just approximate it instead of actually finding the guaranteed cheapest Hamiltonian circuit. And remember, a Hamiltonian circuit is one where every single vertex is visited exactly once, and you end up back where you started, because circuits always begin and end at the same point. So the way that the cheapest link algorithm works is you repeatedly add the cheapest unused edge unless adding the edge creates a circuit that doesn't contain all the vertices, or it makes any vertex have a degree of 3. Because if you think of any Hamiltonian circuit where each vertex is visited exactly once, so it could be like something like that, notice that the degree of your subgraph is always 2. Which makes sense because if you're only visiting each vertex exactly once, you'll go into the vertex once and you'll leave it once. So you have 2 edges that you'll use. And so this is why you want to not have a degree of 3. And you also want to make sure that you actually include all the vertices in your graph. And so that's why you want to make sure that it doesn't create a circuit that doesn't contain all the vertices. So in this example, we could look at it and we'd say, okay, well, first of all, I want to look at what is my cheapest edge. So it looks like this edge is the cheapest because that's $70. Then this one is the next cheapest, and this one is the next. And then the next cheapest one after that, it looks like, is the $100. And the next cheapest one after that is $120. And so this would be the cheapest circuit based on the cheapest link algorithm. Now, it may or may not necessarily be the absolute cheapest Hamiltonian circuit in the graph, but it's a good approximation. And in this case, it actually does end up being the cheapest circuit, but it may not always be in all cases. So let's do another example. So in this one, I'm going to look for the cheapest edge, which in this case would be this edge right here. Then I'm going to look for the next cheapest edge, which it looks like is this one. And the edge that is labeled with a 4, that's the next cheapest edge. However, if I were to add that, then this vertex would have 3 edges leaving it, which won't work for a Hamiltonian circuit because the vertex can only be visited once, which means I have to go into the vertex and leave it. And having a degree of 3 would make that not work because I would like go into the vertex and out of it. But if I use that third edge, then I would have to go back into it. And I only want to visit each vertex once. So I'm not going to use this edge because that creates a degree of 3 on one of my vertices. So then I'll look for my next cheapest edge. And it looks like that is this one. But if I do that, that's going to close up my circuit before I've included all of the vertices. So I'm also not going to use that one. Then my next cheapest edge will be this one. And my next cheapest edge is this one. So the cheapest link algorithm would give me this Hamiltonian circuit. And this is not the cheapest one. because we've done this example several times. And the actual cheapest one that we get with the brute force method is this circuit right here. So again, it's a good approximation, but it may not always give you the absolute cheapest Hamiltonian circuit. So that's how you would do the cheapest link algorithm. Why don't you go ahead and practice it on this one and then restart the video to see how I solved it. All right, so on this one, it looks like my cheapest edge is this one right here. Then my next cheapest edge is this one. Then if I use the 6 edge, because that's the next cheapest one, that would close my circuit before I've included all of the vertices. So I'm not going to use that one. The next cheapest edge is this, so I'll go ahead and do that. Then $8 is the next cheapest, but that would make vertex A have a degree of 3, so I'm not going to use that one. And I'm also not going to use a 9, because that would also make vertex A have a degree of 3. And then, let's see, it looks like the next cheapest edge is this one. And then the next cheapest edge is 11, but that would create a degree of 3. And the next cheapest edge is 13, and that completes my Hamiltonian circuit. And so this would be the circuit that would be given by the cheapest link algorithm. And again, this may or may not be the actual cheapest circuit, but it is a good approximation. So that's how you do the cheapest link algorithm. If you have any questions, let me know.